This is a lecture on the t-distribution. So let's start with what is a t-distribution. I've sketched out a few in some PowerPoint slides here. The t-distribution looks just like the normal distribution, but it has slightly thicker tails depending on the number of degrees of freedom. So in this picture, the red distribution is a t-distribution with 5 degrees of freedom, as you'll see at the top of the page, while the black one is a normal distribution. So what you'll see is that the tails out here are a little bit thicker than the tails in a normal distribution. Now, I said that the t-distribution depends on something called degrees of freedom. This one happens to have 5 degrees of freedom. As the degrees of freedom increase, so let's go up to 10, you're going to see that the tails start getting thinner and it gets closer to the normal curve. Here's 15, 20, 25, 30, and by the time we get to 30, there's not a lot of difference between the normal and the t. Here's 40, it gets even closer. Here's 60, you can barely tell the difference between the two when you have 60 degrees of freedom. When you have 100, the curves are essentially on top of each other. All right, so the t-distribution is just like the normal, except that it has an extra parameter, these degrees of freedom, and those degrees of freedom control the thickness of the tails. So why do we use the t-distribution? Well, let's go back to the normal theorem. So the normal theorem tells us that if you take some random variable minus its mean, divide by its standard deviation, so this is the standard deviation of x bar, that thing has a z distribution, a standard normal distribution. All right, no problem. However, in practice, we don't know the denominator. So we don't know the standard deviation of x bar. So what do? Well, we have to estimate that with the standard error, s of x bar. So, we're not taking x bar minus the mean divided by sigma. Instead, we're dividing by s of x bar. And that creates a problem because s of x bar is a statistic. It's an unknown quantity. We have to estimate it from the data. All right, so since we have to estimate this sigma sub x bar, that introduces some additional uncertainty into this statistic. So rather than just having a random variable here in the numerator and then a parameter in the denominator, when we estimate it with s sub x bar, now we got 2 random variables in this expression, and it's more unstable. So as a result, we need to account for this additional uncertainty, and we do that by using the t-distribution. So remember I said the t-distribution has these thicker tails, and those thicker tails approach those of the normal as the degrees of freedom increase. Okay, so the degrees of freedom are going to be a function of the sample size. So it's always the sample size minus 1 degrees of freedom when we're finding confidence intervals and doing hypothesis tests. So as the sample size gets bigger, the amount of uncertainty introduced by having this additional random variable in the mix goes away and becomes smaller at least, and that's why the tails of the t-distribution get smaller. All right, so a couple points with this. For sample sizes bigger than 40, the t-distribution and the z distribution will be about the same. So it doesn't really matter. So if you have large sample sizes, don't worry about whether you're using a t or a z, because they're going to tell you about the same thing. Let's go to the next slide. So here are details for finding confidence intervals for means. Likewise, if you want to do a hypothesis test in the next chapter, the same rules apply. So when you find a confidence interval, you of course need a z value or a t value. We've been using 1.96 to get a 95% confidence interval. Now we're going to make this a little bit more nuanced. Okay, so if the population is normal and the variance is known, then you use this normal distribution just like we were doing in the previous lecture. However, if the population's normal but the variance is unknown, we're going to use a t-distribution. All right, so remember, the variance is unknown. We have to estimate it from the data with the sample standard deviation s, and that introduces the extra uncertainty, which is why we're using a t-distribution. However, if your sample size is bigger than 40, then the t and the z are about the same, so it doesn't really matter. Okay. A third possibility is that you have a non-normal population, but your sample size is sufficiently large for you to use the central limit theorem, in which case you're going to use the t or the z. I mean, they're about the same. If you have a tiny sample size, a sample size of 10 or something, then you're sampling from a non-normal distribution with such a small sample size. You're going to run into some problems. The central limit theorem isn't big enough. You can't use the t-distribution, since the t-distribution assumes that you have a normal population. Therefore, you're kind of out of luck, and you have to call a statistician. Okay, so just to recap, if you're sampling from a normal population, just use a t-distribution. If you have a non-normal population, but your sample size is big enough, then you can use the central limit theorem. If the population's not normal and you have a pretty small sample size, then you better call a statistician. That's it for the t-distribution. I'll now do some problems.